Alright, so very good evening to all of you. I welcome you on YouTube channel of Unacademy IIT JAM Live. This is your educator Srishti, and in this particular session, we are going to revise important topics of organometallic chemistry for IIT JAM 2021. So we'll be revising these topics with the help of some important questions. So we'll try our level best to just cover all major topics from organometallic chemistry for IIT JAM 2021. Okay. So just confirm this in the chat section if the voice is audible. If you can hear me properly, just confirm it once so that we can start off with our session. Alright, so I think it's audible from my end. So let's start off with our session. So let's take first question. And this is our first question. Alright, so all of you are going with option C. Let's find out, okay? So this is the first complex, and this complex obeys 18 electron rule, okay? So it's given in the question that it obeys 18 electron rule. So you have to predict the correct structure. Okay, so the correct structure of the compound is, so let's start with option A. Now let's take this metal. Okay, this metal. So now this is from chromium family. So chromaton, right? Like this is from chromium family. So basically you have 6 electrons. So if you have 6 electrons on this molybdenum, and this is basically 2 chlorines. Now this chlorine is not bridge chlorine. Okay, so this is terminal chlorine, so it is a 1 electron donor. Okay, so basically 6 from this metal and 1 from this chlorine and 1 from this chlorine. Okay, then this metal is making 3 bonds with this metal. Okay, so 1 2 3, so 3 more electrons from basically this metal bond. Okay, because in one bond you have 2 electrons, so this metal is taking 1 electron and this metal is taking 1 electron. Okay, so 3 from these metal bonds, and this particular ligand, this is having heptacity 5. Okay, so this is having heptacity 5, so plus 5. Okay, now you can see this is 8 plus 6 14 15 and 16. Okay, so it is stated in this question that it obeys 18 electron rule, but this metal is basically obeying 16 electron rule. Okay, so we can cancel out option A, right? So now let's go to option B. So we are just explaining this question in an elaborate format so that you can clarify your doubts and you can revise this topic. Okay, so next is option B. So let's go with this question. So again 6 electrons from this metal, all right, and then you have 2 chlorine ligands, so 2 electrons from 2 chlorine ligands, then again it's a right, heptacity 5 ligand and one metal bond. Okay, so plus 1, so 6 plus 2 8, 8 plus 5, basically it's 13, 13 and 14. Okay, so this is a 14 electron system, so definitely we can cancel out option B. Okay, now let's go to option C. So you can see in option C again 6 from this metal. Now here chlorine is bridge chlorine. If chlorine is your bridge electron donor, so whenever chlorine is basically terminal, so it's 1 electron donor. Okay, it's 1 electron donor. When chlorine is in bridge position, it is 3 electron donor. Okay, so first it will donate 1 electron, then a lone pair of electron. Okay, so now you can see we have 4 bridgehead chlorines. Okay, so if this chlorine, let's go with this side. Okay, we are taking LHS side, that means this half. Okay, so if this chlorine is giving 2 electrons over here, okay, if it's giving 2 electrons, so definitely we have 4 chlorines. Okay, so what we are taking, that 2 chlorines are basically giving 2 electrons and 2 chlorines are giving 1 electron and 1 electron. So this means this chlorine is giving 1 electron to this side and 2 electrons to this side. This chlorine is giving 1 electron to this side and 2 electrons to this side. Okay, so this chlorine is giving 2 electron to this side and 1 electron to this side, and this chlorine is giving 2 electron to this side and 1 electron to this side. Okay, so now let's count these electrons. So 6 from this metal, then we have 2 chlorines, which is basically 2 electron donor, so 2 into 2. Okay, then we have 2 chlorines, which is 1 electron donor, so 2 into 1. Then we have cyclopentadiene ligand, so we have 5 heptacity. Okay, then we have one more metal bond, so 1 electron from this metal bond. Okay, so basically it's 10 10 plus 5, right, 15 16 17 and 18, so it's a 18 electron system. Okay, so this can be your answer. Now we are not verifying this option, we are not verifying RHS, because we have to check option D also. So first I'll check option D, then I'll again come back to this RHS side of this option. Okay, now let's go to option D. So again 5 ligands from this right, cyclopentadiene ligand, and 6 from this metal, 1 from metal bond. Now this is this right bridge position, so let's suppose this is 2 electron donor to this side and this is 1 electron donor, so 2 and 1. Okay, and from this chlorine ligand it's 1 electron donor. Okay, so 5 from this ligand, 6 from metal, 1 from metal bond, 2 from this 1 chlorine ligand, 1 from this chlorine, and 2 from this chlorine. Okay, so what we can say, see this is 6 5 6 and 5 11 12 13 14 15 16, so this side is basically 16. Okay, now if this chlorine is 1 electron donor to this side, so this must be 1 electron donor to this side. Okay, now if this is 1 electron donor, so 2 electron donor. Okay, then you have one metal bond, and then you have one more ligand and 5. Okay, so you can see, and 6 electrons, so this is 11 12 13 14 15 and 16. Okay, so definitely this is not the correct answer, so we'll be going with option C. So just like this, you can verify RHS also. You can see this is 6 from this ligand, then 6 right, 5 from this ligand, 6 from metal, and two chlorines are basically 1 electron donor, and 2 chlorines are 2 electron donor, and plus 1 for metal metal bond. Okay, so both these metals are giving 18 electron system, so definitely option C is the correct answer. Okay, so any doubts to anyone? Is it clear? Just confirm after every question so that we can take the next one. All right, okay. So now let's take next question. Yes, Atanu, this is for IIT JAM 2021. Okay, this is for your JAM examination. All right, okay. So all of you are going with option C. Great, okay. So let's solve this question. So the question is the correct molecular representation of this complex, okay? And we have four given options, and the complexes you have tungsten and Cp2 ligand and two carbonyl ligands, okay? So first of all, we should know that if this complex is basically a 16 electron complex or 18 electron complex, okay? So this coordination number is 4 over here. So this can have 16 electron configuration, or it can have 18 electronic configuration, okay? So if it's 16 electronic configuration, this means the complex, right, should be your square planar. Okay, it is basically in square planar geometry, and if it's 18 electron system, so this means the complex is in tetrahedral geometry. Okay, so if the complex is following 16 electron rule, so the complex geometry is square planar, and if it's following 18 electron rule, the complex geometry is tetrahedral for coordination number 4, specifically for coordination number 4. Okay, now you guys tell me, is it 18 electron complex or 16 electron complex? Is it 18 or 16 electron complex? Right, okay. So this is first of all 18 electron complex. And how we reduce this thing? See, first of all, this is your tungsten. So you must be thinking that this should be 16 electron complex because Z effective is too high. But we have to take 16 electron complexes after chromine. chromium, right? So basically it starts forming from your iron family. Okay, so in most of the cases you will have palladium, platinum, right? And then you can have rhodium, then you can have iridium, right? So these are most of the complexes which follows your 16 electron for electronic configuration. Okay, but chromium family does not follow 16 electron configuration, so this is your 18 electron complex. Okay, so this way you can find out this thing. Now these small points are very important. If you are clear with it, so it's a good thing. If you're not clear, you can just note down all these short points. Okay, so now this is a 18 electron complex. So now tungsten is again from chromium family. So 6 electrons from metal, and we have two cyclopentadiene ring. So we can write X and Y. We don't know about the heptacity. It can have multiple heptacities, right? It can have different values of heptacity. So we can write X plus Y. Okay, then we have two carbonyl ligands. So one carbonyl ligand is a 2 electron donor. So 2 into 2 is basically 4, right? And this is equals to 18. So now 6 plus 4, 10, and X plus Y should be equals to 8. Now if I take a cyclopentadiene ligand, okay, so it can have multiple heptacities as one. It can have one heptacity, it can have three heptacity, and it could have five heptacity. Okay, so we can have 1, 3, 5 as the heptacity value for cyclopentadiene. Okay, now we have to make sum is equals to 8. So it is only possible when you take X is equals to 3 or Y is equals to 3 and the next number is equals to 5. So it's equals to 3 and 5. Okay, so what we can do, first of all, we can cancel option A because it's 1 and 3. So 1 and 3 is not possible. Okay, it's 1 and 5. We can cancel this option. Also it's 5 and 5. It's also not possible. So in option 3 only we have 3 and 5. Okay, so correct answer is option C. Is it clear to all of you? Any doubts in this question? Yes, Ashutosh, all square planar complexes follows 16 electron rule. Okay, square planar complexes follow 6. See, let me give you one right point. So all square planar, okay, all square planar. I have written. I think I have right. Just we have just completed this thing in coordination lectures. Okay, so if you have studied over here, so all square planar complexes follow 16 electron rule, and all square pyramidal complexes also follow 16 electron rule. Okay, then we have tetrahedral complexes and your right octahedral complexes and trigonal bipyramidal complexes. So these all complexes generally follow 18 electron rule. Okay, there can be some exceptions, but in IIT JAM level we can just take this point that these all complexes follows 18 electron right rule. So is it clear to all of you? I hope this question is clear. Now let's move to the second one, next question. No, Ashoka, that complex basically that was your 18 electron complex. Okay, so it's not square planar if coordination number was 4. So this that complex was your basically tetrahedral complex. Okay, it was not square planar, it was tetrahedral complex because we used 18 electron rule, and 18 electron rule and coordination number 4 is applicable to tetrahedral complexes. All right. So in this question, specifically for these type of questions, whenever we have a metal, right, and metal 2 OR6. So for these type of complexes, first we have to check the delta bond formation. Okay, if this complex is making delta bond or not, we have to check this first. Okay, so let's suppose we take very famous example of delta bonds, that is Re2Cl8. Okay, it's very famous that we know in this complex basically we have delta bonds. Okay, so if we have delta bonds, so this thing we have to check in this complex also. Now for this particular complex, that polyelectronic count method is not applicable. Through that method, maybe you are getting correct answer over here, but that method is not valid. Okay, so what you have to do, you have to check if delta bond is forming or not. Okay, so now we know how we can just write down the molecular orbitals for delta bond. So first of all, we have right, delta bond is basically 4 bond. Okay, so basically bond order is equals to 4, so this type of bond is known as delta bond. So 1 sigma and 2 pi and 1 delta. Okay, so we have sigma bond, pi, 2 pi bonds and 1 delta bond. Okay, so if I just look to this energy level, so we know sigma will come first. Okay, so we have sigma, then we have 2 pi, then we have delta. Okay, so again delta star, because this is the most stabilized one, so anti-bonding will be destabilized one. Okay, the most destabilized one. Okay, next is sigma, pi, delta, delta star, and then we have pi star, and then we have sigma star. Okay, so is it clear to all of you? Sigma, pi, delta, delta star, pi star and sigma star. Okay, now let's calculate the electron. So what is the oxidation state of tungsten over here? This is 2x minus 6 is equals to 0. Okay, so if it's 2x minus 6 is equals to 0, so x must be plus 3. Okay, so if x is plus 3, so we have to calculate total electrons. Okay, now just tell me how many electrons we have in this case. How many electrons? So basically it's a tungsten. Okay, so tungsten is having 6 electrons. Okay, and 6 into 2, basically we have 12 electrons. Okay, so 6 into 2, 12 electrons, and for one tungsten the oxidation state is 3, so we have to reduce minus 6. Okay, so basically minus 6, so we have 6 electrons in total. So on metal we have 6 electrons, so we have to fill 6 electrons over here, right? So 1, 2, 3, 4 and 5, 6. So basically we have 6 electrons. Okay, now what was the question? We have to find out metal metal bonds. Okay, so metal metal bond is basically bond order, and bond order is number of electrons in bonding minus number of electrons in anti-bonding divided by 2. Okay, so number of electrons in bonding is 6, a number of electrons in anti-bonding is basically 0, and divided by 2. So 6 divided by 2, it basically gives you 3. Okay, so bond order is equals to 3. So correct answer is option C, that is 3. Okay, so is it clear to all of you? Right, Shamim. Basically, the YouTube sessions have usually have some lag. So whatever I'm teaching live, okay. So I'm getting your answers or responses after some time, okay. So maybe that's why you are facing some lag, okay. So is it clear? Great. So now let's take next question. So this is basically for these type of complexes. Okay, Ashutosh, this is basically for these type of complexes or for delta bonds type of complexes. Okay, first you have to check if right, delta bond is forming or not. If there is delta bond, so that valence electron count method is not applicable over here, or calculation of metal metal bond is not applicable, because from that particular formula the answer would be some different if you're getting a delta bond. Okay, so for these type of complexes, first you have to check like this method. Okay, and you have to calculate like this method. So that method of calculation of metal metal bond is not right, basically working over here. Okay, why we not go by this 18 electron rule? See, in this cases, this is the specific method for these type of complexes. Okay, sometimes we have delta bond, so we have to go with this method. Okay, just to get the correct answer, this is the most appropriate method that you should use for these type of questions. Okay, just remember this complex whenever you'll have this type of complexes M2OR6, so you have to use this method. Okay, just remember this, and you have to use this method. Okay, all right. All right, okay. So according to polyhedral electron count rule, the structure of this is, so you have to predict the structure of this complex: closo, nido, arachno, and hypo. Okay, so these are all given options. So you have to predict the correct structure by polyhedral electron count method. Okay, so first of all, we'll be counting your valence electron, right, of this particular system. Okay, so this is RH6CO16. Okay, so this is basically from your cobalt family. Okay, this is basically from your cobalt family. So now if this RH is how many d electrons in the system? Basically we have 9 d electrons. Okay, so 9 d electrons for this RH, that is rhodium, and we have right, 6 rhodium over here. So 9 into 6 plus we have 16 carbonyls, and for one carbonyl the electron count is 2, so 16 into 2. Okay, so 9 into 6 is basically 54, and 16 into 2 is 32. So this is 4 into 6 and 8. So basically it's a 86 electron count system. Okay, so if it's a 86 electron count system, so we know right, that these type of complexes generally are your octahedral type of complexes. Okay, so from that particular table we can just find out that this is your octahedral type of complexes. Okay, so the next thing is, now if it's 86 type of right complex, next thing is we have to find the structure. Okay, so how we can find it? So valence electron count minus 12n by 2. So with this method we can find out the structure of this particular complex. Okay, so total valence electron count is 86 minus 12, number of metals over here is 6. Basically number of metals are 6. It's like right, so 12n into 6 divided by 2. So now this is 86 minus 72. Okay, so 86 minus 72 divided by 2 is 14 by 2. That will give you 7. Okay, so now the correct answer is 7. So how you can write this 7? So we have 6 metals. So basically this is the formula. Okay, where n represents your number of metals, right, and you have to find this value. Okay, so number of metal is 6, so we have to get 7 as answer. So this is 6 plus 1. Okay, so now if it's n plus 1 type of formation, so we generally represent this as closo. Okay, so if you are getting n plus 1 as in polyhedral electron count, this is closo. If you are getting n plus 2, then nido. If n plus 3, right, then arachno. All right, and if n plus 4, then hypo. And if you're getting simple n, okay, only n, so it's hyper. And right, from n minus 1, basically it's super close. Okay, so like this we can write down these structures. Okay, so is it clear to all of you how we know that this is octahedral? So I think I have shared one table, right, or you can search this table in any standard book. You'll get one table. So we have electron count, and according to that we can find out the geometry of that particular complex. Okay, so from 86 we can find out that this type of complex is basically octahedral, and it's not required in IIT JAM level. Okay, if you want, you can search this table. Okay, so I hope this question is clear to all of you. Great. Okay, All right, okay. So the question is the electrophile pH3C positive reacts with this complex to give a product A. So the product A is formed because Fe is oxidized, alkyl is substituted with this ligand, FePH bond is formed, or alkyl is converted to alkene. Okay. So for this particular question, we should know one term. Okay, and that one term is basically agnostic interactions. Okay. So from your answers, I can see that this concept is not clear. So we'll go in detail. Okay. Now what is agnostic interaction? So let's learn this concept. So right, basically we have this type of bond. Okay. Let's suppose this is our complex Ln M and CH2 CH2 CH3. Okay, if this is the complex LNM CH2 CH2 CH3. Okay, so what we can see that, right, see, I can just erase this one hydrogen and I can write this complex in this way, right? This is one hydrogen of this CH2. So now this is metal, so this is alpha to this metal and this is beta to this particular metal. Okay, no issues, Sonia. I'll try to just complete all topics in this session only, right? So it's a quick revision, so in this time you can revise questions also and concepts also, right? And this much is enough for your exam, because organometallics is a master level topic, so most of the questions are very easy, or the number of questions are very less coming from this topic. Okay, or they are very straightforward. So now this position is alpha and this position is beta. So in the complexes, right, in complexes, if you have beta hydrogen, so you can see you have beta hydrogen in this complex. So those type of complexes which have beta hydrogen, which has basically beta hydrogen, these type of complexes are highly unstable. Okay, these type of complexes are highly unstable in which you have beta hydrogen. So why they're unstable? Because see, this metal is basically making interactions with this hydrogen. This is involved in interaction with this hydrogen. So what's going to happen? This bond is now right, this is broken. Basically this hydrogen gets connected with this metal like this metal Ln. So this will get attached with this metal and now basically you'll be getting alkene. Okay, so basically you'll be getting alkene over here, right? You can get this complex, or what you can get, you can right, basically you'll be getting this type of complex. Okay, so it's nothing but intramolecular oxidative addition. Okay, it's nothing but intramolecular oxidative addition. Whatever I'm telling in this slide only or in this session, that is more than enough. You don't have to search for details of these topics, okay, because these are reaction mechanism and this is not of that importance, but we have to just touch the superficial concepts, okay. So this is your intramolecular oxidative addition. Now what is oxidative addition, I'll be telling you in the upcoming questions. But first thing is, let's suppose if this metal is in zero oxidation state, right? So this metal will go in +2 oxidation state. So let's suppose this metal is in X oxidation state. So now in this complex, this metal will go in +2 oxidation state, okay. So basically this is like intramolecular oxidative addition reactions. So what you have to learn with this term, just only one thing, that if you have beta hydrogens in any complex, so that complex is highly unstable. Simple thing, okay. Now this effect, this interaction or this effect is known as agostic interaction, okay. This effect is known as agostic interaction and it's like covalent interaction. It's type of a covalent interaction, okay. So these points you have to remember, that this name is basically agostic interaction and it's a covalent interaction, okay. And what are the features or what are the results of these type of interaction? That oxidation states increases by +2, okay, and coordination number increases by +2. You can see the coordination number increases by +2. Now you can figure out over here that there is only one increment in oxidation state, because we can write this structure like this, okay. So we can write like this: hydrogen, and this is connected with this CH and this CH, like this, okay. So there is increase in oxidation state by +2, okay. Just these small points: oxidation state is increased by +2, coordination number is increased by +2, and if the complex is 16 electron, so it will go to 18 electron. Just these small facts, okay. So again I'm repeating, so whenever you have beta hydrogens in any complex, that complex is highly unstable. And what are the features of this type of interaction? The features are basically oxidation state increased by +2, coordination number increases by +2, and the 16, if it's a 16 electron complex, so it will go to 18 electron complex, and this term is known as agostic interaction, okay. Agostic interaction, okay, right. Now let's go to this question. So the question was, this is the complex, so you have to get the correct answer, okay. Now you can make sense. So now you can just relate all these points with this particular question, okay. Now definitely it will make some sense. So now let's calculate electron count for this system. So this is 5 from cyclopentadiene and 8 from iron, okay. Then you have 2 carbonyl ligands, so 4 from carbonyl, and what is this ligand? CDMe3. So just have to relate this ligand with CH3 negative, okay. So just like your CH3 negative, you have CDMe2 negative, like this you have to relate. So it's a 1 electron donor, okay. So I'll write +1 over here, and this complex is having +1 charge, so -1, okay. So now you can see 8 plus 4 12, 12 plus 5 17, so it's a 17 electron complex. So now if this complex is having 17 electrons, so this is highly unstable, or definitely it will try to achieve 18 electronic configuration. Now how it can achieve 18 electronic configuration? You can see this is the complex iron, okay, and you have 2 carbonyl ligands like this, carbonyl carbonyl, and you have CD Me3, okay, Me2, like this, and this is basically your this is basically cyclopentadiene. So you can see this is iron, this is alpha, and this is beta. So again you have beta hydrogens in this complex, so this is highly unstable. So what's going to happen? So this system will convert to your alkene, okay. This system will get converted to your alkene, and this hydrogen will be moved to this ion, okay. So basically this will convert like this, okay. You have CD and double bond, and then you have CH2, okay. So there is removal of this hydrogen and this deuterium, okay. So there is removal of HD bond, and this is going to be your final product, Me, okay. So there will be Me, then you have 2 carbonyl ligands and CP ligands. So this is the thing you have to understand, just basic one point. If you have beta hydrogens, so the system is highly unstable, and you can see over here that this is 17 electronic configuration. So if it's 17 electronic configuration, then definitely it will try to achieve 18 electronic configuration, okay. Now you can see, if I just calculate the valence shell electron count, so 2 plus 2 4, and 8 coming from metal, 5 coming from cyclopentadiene, and this is of heptacity 1, and hydrogen is giving 1 electron. Okay, so basically 12, 17, right? So this is basically 12 and 5 is 70. So this is like this particular complex is now your 18 electronic complex. Okay, so is it clear to all of you? Any doubts? Okay, is it clear that pH3C is just acting as electrophile? Okay, so there's a possibility that this hydrogen will leave, and at this particular position this electrophile will attack. Okay, see, this is a possibility that this particular hydrogen, see this hydrogen, this will leave, right? This is electrophile H positive, so it's a possibility that this will attack, or it's behaving as your right, any solvent. So this way you can understand this thing. Okay, so just the main point is you have beta hydrogens. If you have beta hydrogen, the system would be more stable. So alkyl, this alkyl is converted to now alkene. Okay, there is no need to understand this transformation because reaction mechanism is not in your part, but just you have to understand these terminologies, that this is your agostic interaction, and due to agostic interactions alkyl is converted to alkene. So is it clear to all of you? Any doubts? Is it clear, guys? Just let me know if this question is clear. All right, okay. So let's take next one. So I'm not erasing these points, right? So I'm not erasing the ink. So I'll share the PDF if you want after this class, okay? All right. So among the given boranes and heteroboranes, the example which belongs to closo type. So this option A is your borane. Option B is heteroborane because along with borane you have carbon, and option C is also right heteroborane because you have germanium, and in option D it's also heteroborane. Okay. Now we have to find out which belongs to closo structure. So let's go with option A. So option A is basically B5H8 negative. So how I can write B5H8 negative? I can write B5H5, right? And this is B5H5, and how I can write? This is 3 minus and 4 minus. Okay, so what you need to understand before solving out this question, so if the system is like B9, right, BnHn2 negative, so this system is closure. If the system is like BnHn4 negative, then it's nido. And if the system is BnHn6 negative, right, then arachno, and so on and so forth. Okay, so basically this is the format you have to remember. So if this is BnHn, so we can say that the structure is closure. Okay, so this is B5H5 2 negative. Okay, you can see it's BnHn4 negative, so this structure is nido. Okay, now if I go to next option, so carbon. Now we have to go with analogous pair. So carbon is basically it's basically isolobal with your so carbon is having 4 electron deficiency. Carbon has 4 electron deficiency, and boron has 3 electron deficiency, and hydrogen has 1 electron deficiency. So basically you have 3 electrons in boron, 1 electron in hydrogen. So this is also having 4 electrons. That means BH bond is also electron deficient by 4 electrons. Okay, so I can change this BH. I can just replace BH with carbon. Okay, so now this is BH whole twice, and B4H11 2 negative. So this is B6H13 2 negative. Okay, so this is nothing but B6H6. Okay, and we have how many electrons? We have 7, right? We have, so this is 2 negative, and this is B4, so definitely B6. This is B11, so it's 12 and 13. Okay, so if this is B6H6, so we have to take 7 electrons. So now it's 7 and then 9 system. Okay, so definitely this is not your closure form. Okay, so we can neglect this question. Okay, next is this one. So again it's carbon. It's isolobal to carbon because it's from carbon family. So we can just take C3. Okay, so B3, H3, B9 and H11. So this is B9 and this is 12 and this is your 14. Okay, so it's B12, H12 2 negative. So this is now your closure form. You can see 2 negative is coming, B and H and 2 negative. So this is closure. Okay, next is B6H10. So B6H6 4 negative. So this is nido. Okay, so this one is nido, this is nido, and all three options are basically nido. Okay, and only one option is closure. So the correct answer is option C. So I hope it's clear. So if you have any doubts in this question, you can definitely ask. Right, okay. So most of you are going with option D. Let's find out, okay. So the first thing is which you have to remember the correct statement regarding terminal, bridging, carbonyl groups in solid this compound and in this compound, okay. So very first point is there is no need to just find out the structure, but it's always better that you should know the structure of these two complexes, okay. But there is one trick how you can solve this question without knowing structures. So you can see this is cobalt and this is from cobalt family. So cobalt, rhodium and iridium. Okay. So we know one thing that from moving right. So just going in down the group. So this bridging order, okay, or bridging capability basically decreases. Okay. So tendency to form bridging decreases if I go from top to bottom. Okay. So you can see this is cobalt and this is iridium. So due to Z effect, this is basically decreasing. Okay. So now bridging tendency decreases. So definitely in iridium, we won't be having any bridge bonds. But still, it's always better that you should know the correct structure of these two complexes. Okay. Now let's draw these two complexes. So this is cobalt 4 and you have right 12 carbonyl groups. Okay. So first thing is this is basically making cobalt, right? This is your cobalt and you have cobalt over here and cobalt. Okay. So next thing is you have to place 12 ligands. Okay. So 1 2 3 1 2 3 so 3 4 5 6 7 8 9 10 11 12. So this can be one possibility, but we know in cobalt we have bridging type of cases. Okay. So definitely this is not the correct possibility. So in on these two carbonyl groups, right, on this two cobalt, basically you have only two carbonyl groups like this and like this. Okay. So this is carbonyl 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 carbonyl, all these bonds are terminal carbonyl. Okay. Next thing what you have to remember is there is a possibility of bridge bonding, and this is how you can draw these bridge bonds. Okay. So from this carbonyl and this carbonyl you have one bridge bond. All right. So from this carbonyl and this carbonyl you have one bridge bond, and on this carbonyl also you have one bridge bond. Okay. So this is like we have these bridge bonds over here. So now you can count these atoms. So this is 1 2 3 4 5 6 7 8 9 10 11 12. Right. So basically it's 3 and 3 6 7 8 9 10 11 12. Okay. So this is how we can just calculate it, and there is one extra carbonyl over here, right? So you can remove this carbonyl because it's coming 30. So this is the correct structure of this carbonyl. Okay, now we can just join these bonds. So this carbonyl is basically making bond with this right carbonyl. This is making bond with this carbonyl. So this is making bond with this carbonyl like this. It's a tetrahedral type of structure. Okay, now you can see it's a tetrahedral type of structure, and this is the correct structure of this particular molecule. Okay. So is it clear to all of you? Any doubts? Is it clear? So this is the correct structure of this right complex. Now let's go to iridium. So iridium complex is very simple. You have one iridium, iridium, iridium and iridium, right? So this is your tetrahedral complex. So like this, like this, like this and like this. Okay. Now you can just place 6 carbonyl atoms. So this is 1 3 carbonyl and this is 3 carbonyl, and you have then, right, so these 3 carbonyls and these 3 carbonyls. Okay, these 3 carbonyls, yes, definitely, Umesh. So this is isostructural to P4 or CH4. Okay. This is IR4CO12, so this is isostructural to P4 or CH4. Okay, so this is the correct answer. So now the correct option would be the number of bridging carbonyl groups in IR4CO12 is 0. Okay, so basically you have 0 bridge carbonyl centers in this particular molecule. Okay, so is this question clear to all of you? Any doubts? Is it clear, guys? I hope this is clear. Yes, okay, yes, definitely, Ashutosh. That is also the correct way. That is also the correct way. You can calculate number of metal-metal bonds, and according to that, you can draw the structure. Okay, that is also the correct way. This is how we can find out or we can deduce the structure. Okay, that is also the correct way. Okay, now let's go to next question. Okay, it's a nice question. If I take terminal carbonyl, and next thing is if I take a bridge carbonyl, okay, if I take terminal carbonyl or bridge carbonyl, so now we can understand that extent of back bonding is more in bridge carbonyl. Okay, so now we have two metals that is donating electrons to pi star of carbonyl. So definitely if extent of back bonding is increasing, so stretching frequency of carbonyl decreases in bridge bonding. So if I want to compare stretching frequency of carbonyl, so definitely terminal will have more stretching frequency than bridge one. Is it clear? Okay. All right. Okay, so this is the correct thing. Very nice question. Okay, so now let's solve this question. I think most of you have given me the correct answer. Yes. Okay, so all of you are going with option D. So let's solve this question. Okay, the question is basically the correct order of CO stretching vibrational frequency. So we know what is vibrational frequency, mu bar. Okay, so this is 2 pi c k by mu. If we are finding in centimeter inverse, so this is the correct relation. Mu bar is equals to 1 by 2 pi c k by mu, where k is your force constant or bond constant, mu is your reduced mass, c is speed of light, pi and 2 are constant. Okay, so this is the formula. Now we know that this is basically stretching frequency is directly proportional to k and it's inversely proportional to reduced mass. Okay, now let's see these complexes. So if I take these complexes, so carbonyl, this is free carbonyl, and these all are complexes. Okay, so there is back bonding in these all complexes. Okay, so the oxidation state of carbonyl is 0, oxidation state of chromium is 0, oxidation state of vanadium is -1, and oxidation state of titanium is -2. Okay, so if number of electrons are increasing on metal, so if electron density is increasing on metal, so definitely extent of back bonding will increase. So this metal is giving more electrons to pi star of carbonyl. Okay, so if I increase electron density, so this back bonding will increase. If back bonding will increase, so bond order will definitely get reduced. If bond order is reducing, so bond strength will reduce, and if bond strength is reducing, so stretching frequency will reduce. Okay, so number of electrons or number of d electrons is directly proportional to extent of back bonding, and it's directly proportional to bond order of CO. Okay, it's directly proportional to bond order of metal and carbon. Okay, bond order of metal and carbon, and inversely proportional to bond order of CO. Okay, which is directly proportional to bond length of CO, and it's inversely proportional to bond length of metal and carbon. So is it clear to all of you? Any doubts in this question? This relation is very important. Okay, I hope you all are clear with this relation. If number of d electrons are increasing, extent of back bonding will increase. If back bonding is increasing, metal carbon bond order will increase. If metal carbon bond order is increasing, this means bond order of carbon oxygen will decrease. If bond order is decreasing, there is increase in length of carbon oxygen, and if the length of carbon oxygen is increasing, there is decrease in length of metal carbon. Okay, so this is the correct relation, and with this one relation you can solve numerous amount of questions over here. Okay, so correct answer is option D. Now let's suppose we have any complex which is having +3 or +4 oxidation state. Okay, right, so in these type of complexes they will have even more stretching frequency than free carbon. Okay, in +2 and in +3 and +4 type of complexes you will have a more, right, you will have more stretching frequency. But if you have +2 oxidation state, okay, so then it matters, it can have more stretching frequency than carbonyl, or it can have less stretching frequency than carbonyl. But in most of the cases, +3 and +4 will always have more stretching frequency than free carbonyl. Okay, so is it clear? All these points are clear? Any doubts? Okay, great. All right, okay. So let's solve this question. So the value of CO stretching frequencies of one, that is nickel, right, the tetracarbonyl, and second complex is nickel CO3 PMe3, and third complex is nickel CO2 PMe whole twice. Okay. Now this is the complex, and we have to find the correct order of stretching frequencies. Okay, so first of all we can see that in this case we have three carbonyl ligands, right, four carbonyl ligands, and in this complex we have three carbonyl ligand and one PMe3 ligand. In this complex we have two carbonyl ligand and two PMe, right, PMe2 ligand, PMe ligand, okay, PMe3 ligand. Now you just tell me which ligand is basically a better pi acceptor, PMe3 or carbonyl? Which is better pi acceptor, PMe3 or carbonyl? Right, okay. So carbonyl is better pi acceptor than PMe3. Okay. So if you just look to the spectrochemical series, you can find this. Or what we can do, if we are good in basic things, so we can find out that this carbonyl accepts in pi star and this PMe3 accepts in sigma star. Okay, and we know energy of pi star is less than energy of sigma star, so this right, this particular basically this acceptance is better. Okay, so now this is accepting in pi stars and PMe3 is accepting in sigma star. Okay, so next thing over here, so we have four CO ligands and we have one PMe3 and two PMe3 ligand. Okay, so if I'm just going from this complex to this complex, so pi accepting tendency is decreasing. Okay, pi accepting tendency is decreasing. We have a more PMe3 ligand, which is not good pi acceptor if I compare carbonyl. Okay, so we have more better pi acceptor ligands in first complex, so that means it is basically accepting more electron density from metal. If it's accepting more electron density from metal, so the extent of back bonding on one carbonyl ligand will definitely increase. All right, see, the best way to understand this question is like this. Okay, so if we have four carbonyl ligands in this complex, just listen to it carefully, and in second complex we have three carbonyl ligands, and in fourth complex we have two carbonyl ligands. Okay, all right, now what you can understand over here, see, let's suppose this carbonyl is isotopic carbonyl. Okay, I have labeled this carbonyl. This carbonyl is isotopic carbonyl, and we have to talk in terms of this carbonyl only. Okay, so what you can see in this first compound, that you have three carbonyl ligands. Okay, if you have three carbonyl ligands, and in this case you have two carbonyl ligands, and in this case you have one carbonyl ligand. Okay, so number of better pi acceptor ligands are decreasing. Okay, you can see you have this ligand, and if I'm going from left to right, number of better pi acceptor ligands are decreasing. Okay, so what's going to happen in this complex, you have more pi acceptor ligands or more better pi acceptor ligands, so this will take electron density from nitrogen, and finally what's going to happen, the extent of back bonding on this isotopic carbonyl will decrease. Is it clear to all of you? First of all, tell me this, right, reason is clear that why extent of back bonding is decreasing in this NO-CO bond, right? Is it clear why extent of back bonding is decreasing in NO-CO bond? So now if I want to write down extent of back bonding, in nickel and isotopic carbonyl. So the correct order is basically right, third, second and first. Okay, so if this is the correct order of extent of back bonding, so correct answer is a stretching frequency. Okay, so stretching frequency will be in reverse order, 1, 2 and 3. Right, so correct answer is option A. Is it clear? How many of you are not clear with this answer? Just repeat, just tell me once again. Okay, see lovely, what's going to happen in this case? Just pay attention. So these are four complexes. So we know that CO is better pi acceptor ligand than PME3. Now if I'm going from left to right, so we have less number of carbonyl ligands and more number of PME3 ligand. Okay, so if you have less number of carbonyl ligands and more number of PME3 ligands, that this means we have a less number of good pi acceptor ligands. Okay, so only one carbonyl ligand, two carbonyl ligands, three carbonyl ligand. So when we have good pi acceptor ligands, so definitely this will withdraw electron density from nickel. Now if this carbonyl ligand is withdrawing electron density from nickel, so this nickel is having less electron density. Now if it has less electron density, so definitely extent of back bonding will also decrease in this case. Okay, you just have to take one carbonyl as common. Okay, you just have to take one carbonyl as common. So on this carbonyl, the extent of back bonding decreases. If extent of back bonding decreases, so this means this has maximum or this has highest value of stretching frequency. So the correct answer is 1, 2 and 3. So is it clear, Lovely and Bharti? Just tell me, is it clear? If it's not clear, you can let me know. I'll repeat this question after we discuss the complete questions. Okay, once we discuss all questions, I'll again come back to this question. Okay. All right, Ratan. So, is this screen clear? Can you see this question clear properly? Is it clear? Just let me know if the screen is clear. Okay, so I'm just right reading this question. If in case it's not clear to some of you, so I'm just reading the question. So the complex is, see, I'm writing down the complex. This is the complex. Okay, this is the complex, and the question is basically, right, the stretching frequency of nitrosyl in a 16 electron complex. So it's given that this complex obeys 16 electron rule, so you have to find out the stretching frequency of nitrosyl having this empirical formula. So this is the complex, and you have to find out the stretching frequency of nitrosyl if it's if this is obeying basically 16 electron rule. So options are 1850 centimeter inverse, 1650 centimeter inverse, 1950 centimeter inverse, and 200, right, 2050 centimeter inverse. So these are four options. Okay, all right. So it's a factual question. So I'm starting with this discussion. Okay, see. So it's a revision class also. So we are practicing questions and we are doing division. So first, let's understand the properties of nitrosyl compounds. Okay. So everyone, pay attention. So first, let's understand the properties of nitrosyl compounds. Okay. So we are now discussing metyl nitrosyl complexes. Okay, so now we know that if our ligand is basically nitrosyl, so how we can draw molecular orbital diagram of nitrosyl? You can refer MOT structure, okay, which we have discussed in the class. I'm drawing over here. So basically this is your sigma, and this is pi. This is non-bonding, right? This is one non-bonding. This is pi star, and this is sigma star. Okay, so this is basically your structure of nitrogen. Okay, so now let's put electrons. So how many electrons we have to fill? We have to fill is 15 electrons. Okay, so 1 2 3 4 5 6, all right, 7 8 and 9. So basically this is how we can fill electrons in nitrogen. Okay, so now let's understand this thing. So this is the molecular orbital diagram of nitrosyl. So next thing is, we should note that basically nitrosyl can behave as two different types of donors. Okay, so it can behave as, first point is one electron donor, and it can also behave as three electron donor. Okay, if it's one electron donor, so molecule is like N, right, NO2 negative, and if it's three electron donor, it's like NO2 positive. So this is the formation. So if this is the case, so nitrogen is sp2 hybridized, and if NO positive, nitrogen is sp hybridized. Okay, so next thing over here, so this NO plus is basically your pi acceptor ligand. Okay, NO plus is pi acceptor ligand. So for NO, basically HOMO is your this non-bonding, this one. Okay, this non-bonding is your HOMO for NO plus, and LUMO is your pi star. Okay, LUMO is your pi star. So this is the complete information for this NO positive. Now if it's NO positive and it is pi acceptor, so generally it binds linearly. Okay, it binds linearly with complexes, and it is one electron donor, so it binds, right, it basically binds in a bent form. Okay, it binds in a bend way. Okay, so this is the information for NO minus. Okay, so we have third type of nitrosyl also. That is not third type, but definitely these two are your terminal cases. Okay, these two are your terminal cases when nitrogen binds terminally. Right, it can behave as one electron donor and three electron donor. So next case is nitrogen can also bind in a bridge way. Okay, so this can also behave as a bridge nitrogen. Now if this is bridge nitrogen, so nitrogen is double bonded with oxygen, so that means it is connected with two metals like this. Okay, two metals. Now we know at maximum nitrogen can be a 3 electron donor. So on one metal it is donating 1 electron, and on one metal it is donating 3 electrons. Okay, so this is your NO type of formation. So next thing we can understand, so this is the information. So are you guys clear, or right, with all these information? Any doubts to anyone? Is it clear? Right, so this is the complete information for nitrogen NO bonds. Okay, so now let's discuss few more points. So the bond order for nitrosyl, right, is basically in between 2 to 3. Okay, bond order of nitrosyl is basically between 2 to 3. So we have three types of nitrosyl, NO minus and NO positive. When it's NO positive, it's like 3. When it's NO, it's 2.5. When it's NO, right, when it's NO minus, it's 2. Okay, so this is the correct order. Now if I want to arrange the stretching frequency of nitrosyl, okay, so definitely a linear will come first because it's having 3 bond order. Then bent will come, right? So then bent will come, okay, or before bend, right? So definitely, okay, first linear will come and then bent will come. Okay, so this is the correct order of linear and bent. Okay, next is how we can arrange bond lengths of nitrosyl. So we can arrange bond lengths of nitrosyl as bond length of bent is greater than bond length of linear. Okay, we are just comparing bent and linear over here. So is it clear? Any doubts? Yes, definitely. It's donating three electrons. Okay, so this should be 2 electrons. Okay, thank you so much, Atanu, for correcting this thing. This should be 2 electrons. It's basically 3 electrons. It is giving 1 electron to this side and 2 electrons to this side. Okay, so is this point clear to all of you? Any doubts? Is it clear? Okay, so next thing is, now if I have NO, right? If I have NO minus and NO positive, so what's the correct order of bond length? NO minus, then NO, then NO positive. So this is the correct order of bond length. Okay, now again if I want to arrange this in stretching frequency, so the correct order of stretching frequency is NO positive, NO and NO negative. Okay, so this is the information over here. Now if I want to include bridge bonding also, so here I can include it. Okay, let's include bridge bonding also. So in cases of bridge bonding, after bend you'll be getting bridge bonding. Okay, after bend, bridge bonding in stretching frequency. Okay, this is how I can arrange. So if bridge bonding is increasing, the stretching frequency will definitely decrease. Okay, so this is all information, and the next thing over here is how I can just find out correct value of stretching frequencies. Okay, so this is a factual thing, or it's a experimental thing. So you can remember the values. For NO positive, stretching frequency is around 2300 centimeter inverse, and for NO it's around 1875 or 1876. Let's take 76. And for NO negative, it's somewhere between 1500 and 1600 centimeter inverse. Okay, so this is the information for this nitrosyl. Okay, now so this is the complete information for metal nitrosyl bonds, and all these things you have to remember. Okay, now let's go back to this particular question. So now this is the question. So what we have to do, we have to find out valence shell electron count. So this is from a cobalt family. So 9 electrons, x plus 1 plus 4 plus 2, right, and minus 1 is equals to 8. Okay, or what we can say over here, this is basically iridium. So is it a 16 electron complex, or right, 18 electron complex? Is it 16 electron complex or 18? It's given over here, it's 16. But if it's not given over here, then also it's basically iridium. And we know after iron basically we have right, in lower groups we have 16 electron complex, and the steric number is 1 2 3 4 5. So it's a square pyramidal complex. Okay, it's a square pyramidal complex, so generally it follows 16 electron rule. Okay, so this is equals to 16. So now this is 5 6 7 7 and minus 1, so 6. Okay, so 9 plus 6 is basically 15. Okay, so this is basically coming, x is equals to, what's the value of x? This is basically equals to 1. Okay, so 16 minus 15 is equals to 1. So x is 1, so it means that NO is a 1 electron donor. NO is 1 electron donor, so this binds right, binds bent, okay, binds in a bent fashion. Okay, so this binds in bent fashion. So now this nitrosyl is NO negative, right? So this is NO negative, which is a 1 electron donor, and it binds in right, bent fashion. So now we can see this thing, NO positive 2300 centimeter inverse, NO 1876, and for NO negative it's somewhere over 1500 to 1600. Okay, so you can see this value is close to 1600, so we will select option B. Now the value varies according to the complexes, okay, and according to Deegan's metal, this value will definitely vary, but the approximate range is 1500 to 1600. Now you can see only in option B it's close to 1600, so we'll go with option B. Right? Yes, definitely. NO minus will prefer axial position. Okay, it will prefer axial position. Right, axial positions are basically less in S character. So we can say that 1 electron donor will go to axial position and 3 electron donor will go to equatorial position. Is it clear to all of you? Any doubts? I hope this information is right, clear to all of you, this complete information. So this is a quick revision of metal nitrosyl complexes. Okay, so this is quick revision of your metal nitrosyl complexes. Okay, so you can just remember this thing. It's very famous compound, right, and it's square pyramidal. It's square pyramidal, which follows 16 electron rule. So there is one more compound, right, which is basically square pyramidal. There is one more special case, or there is one more special compound for square pyramidal, which basically follows 16 electron rule, and that compound is RuNO2, right, PPH3 whole twice, and Cl. So this is that particular special compound. So you have to remember this compound. Okay, it's also important case. The steric number is 5, so it's square pyramidal, and it also obeys 16 electron rule. Okay, now if first thing about this complex is 16 electron rule, and second thing is, if you'll just find out, you can find out that you have one NO in bent way. Okay, or we can say 1 electron donor and one NO in linear way, or we can say 3 electron donor. Okay, and it's your square pyramidal. It's square pyramidal. Okay, so this is the complete information for metal nitrosyl bonds. Rest you have to apply the basic things of stretching frequency. Okay, so this is all you need for metal nitrosyl complexes. Okay, so I hope it's clear. Okay, one more thing, right, I want to share, just like this information for nitrosyl. Let's learn carbonyl stretching frequency also, because that is also important. Okay, so fine. So basically, when you have free CO, so stretching frequency is somewhere around 2143 centimeter inverse, and when you have CO positive, so stretching frequency around 2184 centimeter inverse, and when you have CO which is connected to BH3, stretching frequency is 2165 centimeter inverse. And okay, when you have bridge type of bonding, so for mu type of CO in bridge cases, stretching frequency is 750 to 1850 centimeter inverse. Okay, now this is the information, just in case they will ask you the factual question. Otherwise the question would be like, you have to compare the stretching frequency, and there is no need of these values. You can compare it because this is free CO, this is CO positive, so definitely it will have maximum value. Then you have CO BH3 because it's giving its right, non-bonding electrons which has anti-bonding characters. Then after this you will have free CO, and then after this bridge bonding CO, right? So in your jam level, a maximum number of time, or most of the time, this is the high probability question. Okay, this is the high probability question, just you have to compare the values. But if in case they will ask you the value, so this is the given values, but I'm sure they won't ask you the information or the data, they will just go for this question. Okay, so you have to compare it. Rajendra, PPH3 is a neutral ligand. Definitely, it's a neutral ligand, but over here we are going by we are going by oxidate, basically it's a neutral ligand. If I just go with oxidative state method, so you can see the charge on ppH3 is 0, so you think it's basically a neutral ligand. Okay, so due to its neutrality the charge is 0, but if I just go by neutral atom method, so ppH3 has lone pair, so it's a 2 electron donor. Okay, ppH3 is a 2 electron donor. Its charge is 0. Whenever you'll be calculating oxidation state of metal, you have to take 0 charge for ppH3. But in case of valence electron count, this ppH3 is a ligand, and always a ligand gives 2 electron donor, 2 electrons to metal. Okay, then only it is basically forming the complex. Right, then only it will form complex with metals. We have very basic things from reaction mechanism, and whatever is required for your IIT JAM, so I'll be discussing respective questions in this session only. Okay, so whatever is required I'll be discussing that. Rest you can practice 18 electron rule questions and other questions. Okay. All right, okay. So this question is basically on carbenes. So if you just go to your JAM syllabus, right? So it's written over here that you have to study carbonyls, okay, and you have to study nitrosyls. You have to study right? Basically, you have to study carbenes, okay. So these three compounds we have to study, and rest the basic reaction mechanism, okay. So carbonyl, nitrosyls, and carbenes, okay. So for this question, Schrock carbenes are triplets and nucleophilic, triplets and electrophilic, singlets, nucleophilic, singlets and electrophilic, okay. So we should know what is basically carbene, okay. So let's just learn some points regarding carbonyl, okay. That is basically I'm telling, okay. Mostly we are discussing this thing. Let's discuss carbonyls, okay. So basically it's metal. Next thing is metal carbene complex. Next is metal carbene complex, okay. So the general representation of metal carbene complex is like this thing, or what can I say, whenever you see M double bonded with any carbon, so this is basically metal carbonyl complexes, okay. Now if I just write down all parts of this complex, so this part CX2, CX2 is basically CXY, it has 2 electrons, so this is your carbene, okay. We know what is carbene. the simple representation is CH2, and it's an electron deficient, electron deficient molecule having 6 electrons. Okay, so this is your carbene. This is your carbene part. Okay, this is your metal, and these are basically n number of ligands, and we call these ligands as spectator ligands. Okay, so we can call that these ligands are basically spectator ligands, and this is your carbene X and Y. Okay, so basically carbene is sp2 hybridized, and it's a 6 electron compound. Okay, so this is your carbene, and on this particular basis we can just subdivide carbenes into two forms. Okay, one first is your Fischer carbene, right? First is Fischer carbene. These are name of the scientist, and second one is Schrock carbene. Okay, first one is Fischer carbene and second one is Schrock carbene. So we can say Fischer carbene is electrophilic carbene. Why it's electrophilic, we'll learn that. And Schrock carbene is nucleophilic carbene. Okay, so Fischer carbene is electrophilic carbene and Schrock carbene is nucleophilic carbene. Okay, now let's first learn what is Fischer carbene, or let's go with differentiation of Fischer carbene and Schrock carbene. Okay, so let's learn the points and the differentiation between Fischer carbene and Schrock carbene. Okay, so we know the general representation of carbenes are Ln, M double bonded with carbon, X and Y. So this is the general representation of carbenes. So we can say, if I want to differentiate between Fischer carbene and Schrock carbene, so let's start with oxidation state. Okay, first point is oxidation state. Okay, so now if I compare Fischer carbene and Schrock carbene, so in Fischer carbenes the oxidation state should be less than +2, or it can be equal to +2, and in case of Schrock carbenes oxidation state should be greater than 2. Okay, so if the oxidation state is less than 2 or equals to 2, so these type of compounds are basically Fischer carbene, and in Schrock carbene the oxidation state of metal should be greater than 2. Okay, so this is first point. And now the next point is on the basis of your X and Y ligands. So X and Y ligand, nature of X and Y ligands. Okay, so in case of Fischer carbene, basically X and Y ligands should be pi electron donor. Okay, they should be pi electron donor, and X and Y ligands in this Schrock carbene, basically they should be non-pi electron donors. Okay, non-pi electron donors. Now if I take third classification, so third point over here is nature of your spectator ligands. Okay, what is the nature of these spectator ligands? So in Fischer carbene the spectator ligand should be pi acceptors. In Fischer carbene the spectator ligand should be pi acceptors, and in case of Schrock carbene the spectator ligand should be non-pi acceptors. Non-pi acceptors. So we know all type of ligands are basically sigma donor. So what we can write down, these spectator ligands can be they should be sigma donor as well as pi acceptors, and these spectator ligands should be sigma donor but not pi acceptors or non-pi acceptors. Okay, so this is all about metal oxidation state, X and Y ligands on carbene part, and your spectator ligands. Okay, now let's understand one thing. Just see this this particular representation, and let's discuss Fischer carbene. So the thing is, these ligands should be pi electron donor. The metal should be in low oxidation state, and this ligand should be pi acceptors. So if they are pi donor, so they are donating electron density in this particular direction. These are basically metals of low oxidation state. So if they are donating electron density, so this means electron density on metal on this carbon is basically increases. So this metal is basically in low oxidation state, so this will take electron density from this carbon. Why it's taking electron density in this particular direction? Because all these spectator ligands are basically your pi acceptor ligands. Now these spectator ligands are pi acceptor ligands, so this is taking electron density from metal. So this metal is taking electron density from carbon. So now for this process you should have electron density on carbon. So that's why these two ligands are basically pi donor type of ligands. So again I'm repeating, this pi donor ligands are giving electron density on this carbon. This metal is taking electron density from this carbon, and these ligands are pi acceptors, so they are taking electron density in this direction. So what is the direction of their electron shift? The direction is basically right to left. Am I right? The direction of electron shift is right to left. Okay, so this is the direction of electron shift. Now you can see due to this particular process, because electron is going from right to left, so this carbon is electrophilic carbon. right? This carbon is electrophilic carbon. So this is the reason that why we call Fischer carbons as electrophilic carbon. Now let's take Schrock carbons. So now you can understand that basically these type of right XY ligands are non-pi donors, so they are not giving electrons on to carbon. Okay, so basically these are sigma donors and they are non-pi acceptor ligands. Okay, so now what is actually happening? This is your nucleophilic carbon because they are sigma donors but not acceptors. If these ligands are giving electron density on metal, so on a metal the electron density is increasing and oxidation state is high, so definitely it will give electron density on this carbon. Okay, so what's going to happen? Comparatively this carbon is having more electron density, so this type of this type of carbon is basically nucleophilic carbon. Okay, so Schrock carbon electron density shift is basically left to right. Okay, this electron shift is basically left to right and this type of carbon is known as nucleophilic carbon. Okay, so is it clear to all of you? This point is clear? Just let me know if this is clear. Is it clear? All right. Okay, so the next thing is basically if this if this system or if this Fischer carbon is electrophilic in nature, so generally these type of complexes are basically 18 electron complexes. Okay, these type of complexes are 18 electron complexes, and we have these type of metals right, which generally form your Fischer type of carbon. Okay, we have this RuOS, okay, ferrous and chromium family. Okay, so these type of metals generally they form your Fischer type of carbon. Okay, now if I take Schrock carbon, so generally 18 electron complexes won't show your Schrock type of carbon. Okay, now if I want to write down the metal which is basically involved in Schrock type of carbon, so in most of the cases it is vanadium, then this metal and sometimes titanium and molybdenum, right? So in most of the cases these three metals show your Schrock carbon and all these metals show your Fischer carbon. Okay, so this is the classification of your Fischer and Schrock carbon. Now let's go back to this question, and yes, one more important thing, Fischer type of carbons are basically your singlet carbon. Okay, they are basically singlet carbon, and these type of carbons are basically triplet carbon. Okay, so now let's go back to the question. So the question was Schrock carbons. Okay, so now we know Schrock carbons are nucleophilic in nature. First point, they are nucleophilic in nature and they are triplets. Okay, so the correct answer is option A. So for Schrock carbon, option A is correct answer. And if I have to ask for Fischer carbon, so it would be singlet and electrophilic, option D. Is it clear to all of you? Any doubts to anyone? I hope this question is clear to all of you. So this information is written. So I would share the slide. There is no need to write down the information. I'll definitely share the slides. Okay. So next question is the correct order of energy levels of d orbitals and ferrocene. So this is the question. The correct order of energy level of d orbitals in ferrocene. See, most of you are clear with 18 electron questions and 16 electron question, okay? Just all this information is very new for those aspirants who are not clear with this information, okay? So this is all thing we are discussing over here is more than enough for your exam, okay? You just have to revise this portion and practice a lot of questions. Right, okay, so let's discuss this question. The correct order of energy levels of d orbitals in ferrocene, okay? So now we need complete information for ferrocenes, okay? So what is basically ferrocene? It's Cp2 Fe ligand, okay? So whenever we just change this metal, so it's an example of ferrocene only, right? So this particular complex is known as your ferrocene, okay? Now if this complex is ferrocene, so we can have more examples. We can have Sep2Mn, right? We can have chromium, we can have any metal, right? So this is an example of ferrocene. Ferro means iron, okay? So when the metal is iron, so we call it as ferrocene, okay? So what is basically the splitting pattern, okay? D orbital splitting pattern of ferrocene. D orbital splitting pattern of ferrocene, okay? So d orbital splitting pattern of ferrocene is like this. You have dxz and dyz. So you have dxz, dyz over here. Then you have dz square, right? And then you have dxy and dx square minus y square, okay? So this is the pattern of your ferrocene. Now what all information you have to remember for ferrocene? So this is delta 1 and this is delta 2, okay? In most of the cases, in most of the metallocene compounds basically, right? So if I change this metal, so these are called metallocene, okay? So in most of the metallocene compound, del 2 is basically greater than your del 1. In most of the metallocene compounds, delta 2 is greater than right, del 1. So it means if this value is greater than this value, so it means right, always there is pairing, right? You have to pair electrons. So first of all you have to fill first electron, right, second electron, third electron, fourth electron, fifth electron, sixth electron. Then after 6 electrons you have to fill electrons in dxz and dyz, okay? So I'll write down this thing over here. First electron, second electron, third electron, fourth electron, fifth electron, first, second, third, fourth, fifth and sixth, okay? Or this is the correct order: first, second, third, first, second, third, fourth, fifth and sixth. So this is how you have to fill up these electrons, okay? So first, second, third, fourth, fifth and sixth. So this is the correct order of filling up these electrons, okay? But there is one exception only, and that exception is particularly your Mn ferro, Mn metallocene, okay? So there is one exception only for this particular complex, okay? That is Cp2Mn. Only for this complex, what is the pattern? Basically, delta 2 is approximately equal to delta 1, okay? So they have comparable energy, and there is one difference over here in the electron filling, okay? And the difference is first electron, second electron, third electron, fourth electron, fifth electron, sixth, seventh, eighth, nine, and 10. Right? Yes, definitely, right? Delta, see, in this case, this is 2, right? Delta 2, so I have written delta 2 over here. So delta 2 is greater than delta 1. If delta 2 is greater, this means CFSE is higher. If CFSE is higher or splitting energy is higher, so pairing will happen. Okay, that means pairing energy is basically less than your delta 2. So pairing energy is less, this means pairing will happen. Okay, is it clear, Tanu? So this is the electronic pattern 1 2 3 4 5 6 7 8 9 10. Okay, this is for particularly this ligand. Okay, so now if I have to fill electrons for ferrocene, now let's fill electrons for ferrocene. So how many electrons I have to fill? Just quickly tell me how many electrons I have to fill for iron. We have to fill 6 electrons. Okay, so 1 2 3 4 5 and 6. So this is the pattern of electron filling in ferrocene. Okay, in ferrocene or in any metal case except manganese. Okay, but in this case you have to fill 5 electrons. So 1 2 3 4 5. Okay, so this is the case. Now if I have to write down the correct order of energy for ferrocene, so definitely you have dxz and dyz, then you have dz square, then you have dx square minus y square, and this one. Okay, so correct answer is option 1. But if you want to write down the electron filling, so this is the correct pattern. Okay, so is it clear to all of you? Any doubts? Is this question clear? Okay, fine. All right, so now let's take the next question. It's basically MSQ question. Okay, so you have MSQ question, more than one option is can be your correct answer. All right, okay, right. So let's solve this question. So the question is the incorrect statements about Z salt is. So option A is Z salt is diamagnetic. The oxidation state of platinum in Z salt is +2. All the platinum Cl bond lengths in Z salt are equal. And option D is C bond length of ethylene moiety in Z salt is longer than that of your free ethylene molecule. Okay. So let's discuss this concept. So the question is of basically Z salt. Okay. Now, what is the formula of Z salt? This is the formula K. We have platinum, Cl3, C2H4 ligand. Okay, or the structure of Z salt is platinum. It is connected with three chlorine bonds and one double bond like this. Okay, so this is K platinum Cl3 C2H4. This is platinum ClCl and this particular bond. Okay, so first point we have to see for a Z salt is platinum is present in +2 oxidation state. Okay, C +1 or right, let's take this as X for platinum, -3 is equals to -1. Okay, so this is +2, so that means platinum is present in +2. Okay, next thing is it's a square planar complex. We know platinum again, it's a square planar complex. So if it's a square planar complex, it is following 8-16 electron rule. Okay, and if it's square planar complex is 16 or 18, in most of the cases they have filled right BMOs. So if it's right square 16 or 18, always it will prefer fill BMOs. Okay, so this is your diamagnetic complex. Diamagnetic complex. So now next is if I want to compare the bond lengths of this Z salt. So if this bond length is L1, right? If this particular bond, or let's name this as first bond length, okay? And this is second bond length. This is third bond length, and this is fourth bond length. Okay, so if I want to write down the correct order of bond length, so correct order of bond length is fourth, right? So fourth is the basically longest bond, and then you have third equals to second, then you have first. Okay, so trans to this ethylene bond is longer. Okay, so this is your longer bond, so this is the correct order of your bond length. Okay, and the next point is this ethylene molecule is basically perpendicular to PTCl3 plane or perpendicular to plane of the molecule. Okay, so this is the correct orientation of your square planar complexes. Okay, so this point you have to remember for your Z salt. Okay, next concept is when basically you have free alkene. When we have free alkene, right, if we have free alkene, so we know that alkene nature is basically nucleophilic. This alkene is nucleophilic in nature if we are taking isolated alkene or free alkene. But in this metal complex, we know that this alkene is basically donating electrons to metal because it's a ligand. And what's the primary role of ligand? It's first always a sigma donor. Always all type of ligands are sigma donor. Then after sigma donation, it can be pi donor or pi acceptor ligands. Okay, so now we know it's a sigma donor ligand, so it's donating electron density to platinum. So due to this, you have partial positive character on alkene. So now if I take metal complexes, so now this alkene is basically electrophilic. So we know that standard nature or the initial nature of this alkene is nucleophilic, and now it's behaving as electrophilic. So whenever there is change in the polarity, so that particular term is known as unpolar. Okay, that particular term is known as unpolar. So there is change in the polarity, or there is change in reactivity or change in sign of alkene. So first it was nucleophilic, now it's electrophilic in nature, so there is unpolar effect, and this term is basically change of polarity, okay, of alkene in metal complexes. And next point over here is, right, so this is all about alkene. Okay, so definitely if it's your alkene, so it is a pi acceptor ligand. First it's a pi donor ligand, then it's a pi acceptor ligand. So this is all about your ZZ salt. Okay, now let's go back to question. So the question is, the incorrect statement about ZZ salt is, first is it's diamagnetic, it's correct. Second is the oxidation state of platinum in Z salt is +2, it's also correct. All the platinum Cl bonds in Z salt are equal. No, it's this is the incorrect statement. And option D is Cc bond length of ethylene moiety in Z salt is longer than that of your free ethylene molecule. Now, if you see, it's a pi acceptor ligand. Definitely, it is giving electrons to metal. Okay, it's a sigma donor. But after sigma donor, right, basically it's taking electrons back from this metal. Okay, it's a pi acceptor ligand. Now, if it's a pi acceptor ligand, so there is there is back bonding, and if you're adding electrons and anti bonding, so definitely bond length will decrease. Okay, so bond length will increase if you are adding electrons in back bond, right? Anti-bonding molecular orbital, if you're adding electrons in anti-bonding, bond length will increase. Okay, so CC bond length of ethylene moiety is Jesus salt is longer than your free ethylene molecule. So it's basically they're asking CC. So if there is right back bonding, so if there is back bonding, right? If there is back bonding, so you're adding electrons in anti-bonding molecular orbital. So you are decreasing bond order, but you are increasing bond length. Okay. So CC bond length of ethylene moiety in Z salt is longer than your free ethylene. So this one is also correct option. Okay. So according to the question, we have to figure out incorrect options. So only C is your incorrect answer. So is this term clear to all of you? Any doubts? Is it clear? Right? No issues. Okay, no issues. If it's incorrect, so correct answer is C. If you have to figure out the correct options, so answer would be A, B and D. So is this question clear to all of you? Any doubts? Okay, fine. So this is all information about your Z's salt. Now one more thing that is important. If I'm taking, if I'm let's suppose we have Z's salt, and from platinum I'm going to palladium. I'm replacing platinum with palladium. Okay, I'm replacing platinum with palladium. So what's going to happen? Right. So what you have to tell? You have to tell bond length of ethylene moiety or bond length of ethylene molecule in your complex. Okay. So if I'm changing from platinum to palladium, we know that ethylene is basically pi acceptor. So it's basically accepting in LUMO. From metal, it's accepting in LUMO, ethylene. Okay, and this metal is basically donating the electrons to pi star. Okay, so your metal is basically your HOMO. So metal is HOMO and ethylene molecule is your LUMO. Now, which particular process is more feasible or the extent of back bonding is higher in platinum or in palladium? How we can compare it? We know, if I just go back to electronegativity principle, so palladium is more electronegative than platinum. If palladium is more electronegative than platinum, so palladium molecular orbital will be like this and platinum molecular orbital will be like this. Okay, so if you're increasing the electron negativity, so in energy will decrease in molecular orbital diagram. So this is of palladium, this is of platinum, and this is your ethylene. So this back donation is more feasible. Okay, from platinum to ethylene, this back donation is more feasible. So this means if back bonding is increasing, if I have to write down the back bonding order, so that would be of platinum and then palladium. Okay, and if back bonding is increasing, so CC bond length will definitely decrease. Okay, so CC bond length in palladium, right, in basically platinum, if back bonding is increasing, so CC bond length will increase. Okay, if back bond is increasing, so that means CC bond length will increase, and in case of platinum, you'll be having longer bond length than palladium. Is it clear, all of you? Any doubts? Is this point clear? Here platinum is D8 system, so it should be paramagnetic. See, first thing is it's square planar. Okay, and the oxidation state on platinum is +2, right? So it's like definitely it's D8 system. Okay, definitely it is D8 system. But if I want to just write down this electron splitting diagram of platinum, okay, so how I can write down electron splitting diagram of square planar complexes? So so there's a change. Okay, so first of all you will have dx square minus y square. Okay, first of all you will have dx square minus y square, then you have dxy. Okay, so then you have dxy, and there's a change that first of all you will have dxz and dyz, and there is dz square. Okay, so this is the electron filling pattern. So 1 2 3 4 5. Okay, so then you have 1 2 3 4 5, 1 2 3 4 5 6 7 8. Is it clear? Is it clear? Right, Bharti, is it clear? If you just fill the electrons in your square planar complexes, just you know the splitting, right? I have told you that how we can fill electrons in square planar complexes in case of 5D series. Okay, so you just fill the electrons, you'll see that all electrons are paired. Okay, so this complex is diamagnetic. Okay, this complex is diamagnetic. right? Is it clear to all of you? Any doubts? Okay, I think it's clear. Fine, I think this question is clear. So now let's go to the next thing. So one more thing, just like your metal alkene complex, you have metal alkyne complexes also, right? You have metal alkyne complexes also, just like your metal alkene complex, okay? And in metal alkyne, basically in place of your alkene, you have alkynes, okay? So this is your alkyne, right? Now we know this is sp hybridized, so alkyne can behave as 2 electron donor also, and it can behave as 4 electron donor also if it's donating electrons from one pi bond. So if it's a 2 electron donor, if it's donating electrons from 2 pi bonds, it's a 4 electron donor, okay? So this is your metal alkynes complexes, okay? Now the next thing is basically, right, if I just write down two complexes over here, this is this complex chlorine chlorine, and then you have chlorine and this alkyne, okay? And this is one complex like this, okay? Or let's write down pph3, okay? So what you can understand that it's a 16 electron complex, and this should be also 16 electron complex, but there is vacancy over here, right? The coordination number is not 4. So generally what happens in these type of complexes, this will bind to this alkene like this will bind to this alkyne like this, okay? So this binds to this alkyne like this, pph3 and pph3, right? So now it has converted this alkyne to basically right, metallo cyclopropene complexes. Cyclo, okay? It has converted this alkyne to cyclopropene complexes, okay? So this is your this structure and this structure. This is first structure and this is second structure. Now if I want to compare electron density, so we know electron density in second structure will be greater than first structure. How? You can see that on this complex the oxidation state is basically +3, okay? The oxidation state is +3, and over here the oxidation state is 0, okay? Or you can say, if I just convert this to ppht, so oxidation state is +2 and oxidation state is 0, so definitely electron density on second complex metal is greater than first complex metal, okay? Now if I compare back bonding character or extent of back bonding in first and second complexes, so you can see with this alkyne, basically it's making two bonds in second complex, and in first case it's making one bond, okay? So back bonding extent is greater in second than first, okay? Now if I compare which carbon is having more sp2 characters, so definitely you can see now it's alkene, so second complex is having more sp2 characters, but now in this case it's alkyne, okay? So it's having sp characters. Next is bond order of carbon carbon, okay? Now if there is more back bonding in second complex, so bond order is less in second complex, okay? So bond order of first complex is greater than bond order of second complex, okay? So I think this is also clear. So this is one comparison between your metal alkyne complexes, okay? Now let's go to next question. All right, so before this question, let's discuss some other question because I have to use some basic name reactions in this question. So for that, we need to understand those name reactions first. Okay, so let's go to different question. Okay, and fine. So let's go to this question first. Let's explain this question. Then we'll again solve the previous one. Yes, Atanu, I'll be discussing the things for this name reaction. Okay, so just you have to complete this portion. Okay, you don't have to just study deep in name reaction. Just the basic terms are required and the function. All right. So let's discuss this question. Okay. So basically, in this particular question, what we have to do, we have this reaction. Okay, and we just have to we have to figure out that this reaction is an example of which type of reaction. Okay. So if this is the complex Mn and it has five CO ligands, right? CO, 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 and your Me ligand. And basically, you are adding one CO ligand, and the product is you have five CO ligands and COMe, right? So you have five CO ligands and COMe. Okay. See, in this question, so this is one type of this is one type of name reaction for organometallics, and the name reaction is migratory insertion reaction. Just the term is required and the function. Okay, so migratory insertion reaction. So in these type of reactions, what happens? So this carbonyl basically migrates to this position. Okay, this carbonyl migrates to this position and it will convert the system basically to CO, 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 and at this position you have space now. It's vacant site, and this is COMe. Now this is vacant and you are adding one external ligand, so this ligand will take this position and basically it will convert this ligand to this complex. Okay, so now let's suppose this ligand is isotopically labeled. So now in this complex this CO will be here and this is your isotopically labeled carbonyl. Okay, so you can see first there is migration and then insertion. Okay, so migratory insertion reaction. Okay, so this term is known as migratory insertion reaction. So only this type this name you have to learn. This is migratory insertion reaction. And second point you have to learn over here is right, let's suppose this is basically your 18 electron system. Let's take an example. This is 18 electron system. Okay, so now you can see this is not 18, now this is 16 electron system. Okay, you can calculate 1 2 3 4 5 5 into 2 10, 10 plus 6 16, and 16 plus 1, basically it's a 18 electron system. Okay, if it's a 18 electron system, so this complex would be 16, but again it would convert to 18 electron system. So the complex is not changing from 18, it is basically to 18 only, right? So the complex is from 18 to 18, but there's an intermediate from 16. Okay, so next point over here is there is no change in oxidation state. You can see that the oxidation state is basically +1 and the oxidation state is same in this complex also, right? So there is no change in the oxidation state. So the correct answer for this question is basically migratory insertion reaction. Is it clear to all of you? Any doubts? Is it clear? Right, okay. So in this question, so definitely you can see that pi donor ligands are increasing. So if pi donor ligands are increasing, so there is more back bonding in product than in reactant. So according to this concept, the stretching frequency should decrease in product. But you have missed one point, and that one point is oxidation state. Just see. The oxidation state is +1 in this complex, and the oxidation state is basically a +3. Okay, so you can see that oxidation state is changing, right? And we know +3 is very basically it's very high oxidation state, and in high oxidation state compounds there is very minimum back bonding. Okay, so you just have missed this oxidation state concept, and you can see the oxidation state is increasing. So you have to apply this concept only when oxidation state is same, so you can see the ligand nature. Okay, but here the oxidation state is increasing, so if oxidation state is increasing, you have to give more preference to oxidation state. Okay, so the oxidation state is from +1 to +3, that's 2 unit change. Okay, so that is a very high change, basically appreciable change, so you have to give more preference to +3 oxidation state. So +3 oxidation state, in +3 the back bonding will be minimum. So the correct answer is right, CO, stretching frequency in product is greater than CO, stretching frequency of your reactant. Okay, so this is the correct answer. Now this type of reaction is basically known as your oxidative addition reaction. Okay, this reaction is basically known as oxidative addition reaction. Now basically we have two types of reactions. One is oxidative addition reaction, right, and one is reductive elimination reaction. Okay, one is oxidative addition reaction and one is reductive elimination reaction. So what's the difference between oxidative addition? You can see first point is oxidation. So if there is oxidation, so what we can say that there is oxidation change from in basically there's a +2 units oxidation state. If the oxidation state is +1, so in product it will go to +3. If its oxidation state is +2, it will go to +4. Okay, so there is oxidation, there is change in oxidation state by +2. There is change in coordination number by +2. There is change in d electrons. So basically d electrons reduces by 2 units, and electronic configuration also reduces by 2 units. How? Let's suppose this is our complex ligand and metal, and we have to add this ligand on this complex. Okay, so now if metal is in 0 oxidation state, so it will go to +2 oxidation state. Now you can see if these two ligands are charged ligands, so basically it's basically a +2. Okay, so first point is the oxidation state is increasing by 2 units. You can see the oxidation state is 0, 2. Coordination number increases by 2 units. Coordination number is, let's suppose, 4 over here, so there is increment of 2 coordination number. D electrons decreases by -2. Definitely if oxidation state is increasing, so D electron reduces by -2. Okay, if we have 10 D electrons, so in the product it will be 8 D electrons. Okay, and electronic configuration reduces by 2. Yes, definitely if the electronic configuration is D1, so we'll be having Dn minus 2 electronic configuration. So these type of reactions are basically oxidative addition reaction. Okay. So next point in oxidative addition reactions are basically right, the points for metals and ligands. So if we want to do oxidation, definitely metal should be in low oxidation state. Am I clear? If you want to do oxidation, metal should be in low oxidation state. Okay. It should have non-bonding electron density. Then only we can oxidize the metal. Okay. We have to increase the oxidation state. Third point is final oxidation state should be stable, right? Final oxidation state should be stable. Then only the product will form. If it's iridium, so we know that this is the minimum oxidation state and it will go to iridium plus 3. So this is a stable oxidation state for iridium. Okay. If we have platinum plus 2, so it will go to platinum plus 4, right? If we have iron plus 2, so it will go to iron, right, plus 3. So there is no increment of plus 2, so this is not oxidative addition reaction. So iron won't give oxidative type of reactions. Okay. So there is increment of plus 2 oxidation state. Okay. And next point over here is most of the cases D8 and D10 systems basically shows oxidative addition reaction, because we need more electron density on metal. Okay. So low oxidation state or more electron density. So what all are the complexes? So these are complexes. So most of the cases, these all complexes shows oxidative addition type of reaction. Okay. So these are some examples of complexes which shows oxidative type of reaction. Okay. So D8 or D10 systems. And the next point is, so D0 and D5 system won't show your oxidative addition reactions. Okay. Because we need electrons for oxidation. So D0 won't show. And D5 we don't have enough electrons in the this complex, so it's not possible with D5 system also. So D8 and D10 most of the times will show, and D0 and D5 won't show. Okay. So this is about the oxidative addition reaction. Okay. So let's go to now a reductive elimination reaction. So this is just opposite of oxidative addition reaction. Okay. Now if I just learn reductive elimination reactions, so definitely change in oxidation state should be -2. Right. So this is just opposite of your reductive elimination reactions. Okay. So the next thing over here is, so this oxidative addition reaction is basically your enthalpy driven process. Enthalpy driven process. Okay. What's the driving force for oxidative addition reaction? Enthalpy. Okay. You can see there is bond formation. So if there is bond formation, so it means that it's enthalpy driven process, because it's exothermic process, right? So if you are releasing amount of energy, that means this is spontaneous process. Okay. So this process is enthalpy driven process, and reductive elimination process are basically right, this is your entropy driven process. Okay. This is basically your entropy driven process. You can see the entropy is increasing. So if entropy is increasing, this is your driving force for spontaneity. Okay. So oxidative additions are enthalpy driven process, and reductive eliminations are basically entropy driven process. Okay. So this is the major difference between your oxidative additions. Now let's know about reductive eliminations. Okay. Let's know about reductive elimination. So these are some points that oxidation state should be -2. Coordination number changes by -2. That means it reduces by 2 units. The electrons, it increases by 2 units, and your electronic configuration also introduces by 2 units. Okay. So next thing is basically most of the times your rhodium plus 3, iridium plus 3, right, and palladium 4 and platinum 4. So these all complexes show reductive elimination. That means most of the times D6 type of configuration. Okay. And if I just want to talk about metal, so metal should be in high oxidation state. Definitely we have to reduce. Okay. We have to give electrons to metal, so it should be in high oxidation state. So right, if I just take leaving group, because we have some leaving groups, so that should be electron rich. Okay, so we have to just accept electrons, so we have to just mate leaving group leave the surface, and the leaving group should be electron rich. Okay, and the spectator ligands, okay, and the spectator ligands definitely they should be pi acceptor ligands. Okay, because we are increasing electron density on metal, so we should have some right ligands that should accept the pi electron density back. Okay, so spectator ligands should be pi acceptor ligands, and right there should be steric hindrance in the molecule. There should be steric hindrance in the molecule. Why we need steric hindrance? Because we basically want to leave two groups. Okay, so if there is more steric hindrance, so instability would be there and the leaving groups will leave the surface. Okay, so this is all points for a reductive elimination. So how I can conclude this point, if I want to make a differentiation in oxidative addition reaction and reductive elimination reactions. Okay, so in oxidative addition, basically oxidation changes by +2 unit, and oxidation state changes reduces by -2. Okay, so if you have to increase the oxidation state, so oxidation state should be low. Okay, it should be low, and if you have to increase the oxidation if you have to increase the decrease the oxidation state, so oxidation state should be high, right? So this is the major difference between your reductive elimination and this type of groups. Okay, just like we discussed rate of your reductive elimination reactions, so similarly we can discuss rate of your oxidative addition reactions. Okay, so if you want to increase rate of oxidative addition reaction, so definitely steric hindrance should be less. If there is more less steric hindrance in the molecule, then only two groups can add on this particular complex. Okay, and the pi acceptor ligand should be less. In the structure, you should have less pi acceptor ligands because you have to increase the oxidation state. Okay, so if you have to increase the oxidation state, so pi acceptor ligands should be less in number. Okay, so this is all about the differentiation in oxidative additions and the differentiation in reductive elimination reaction. So is it clear to all of you? Any doubts in this question? Is it clear? Okay, all points are written in the slide. You can read these points, and if you feel you have some doubts, you can let me know on WhatsApp. Okay, or you can let me know in Telegram channel. You'll find the link in the description box. Okay, you can join that Telegram channel and you can message me from there. Okay, so next is this question. Adanu, in the description box, you'll find a link of Telegram channel. Okay, a link is given in Telegram channel. It's like right, Unacademy underscore SBATRA. So you'll find one link. You can just join that Telegram channel. I'll post the PDF over there. Okay, or the basically the link is like this only, right? So you can just search over Unacademy, or you can just find the link from description box. So this question is very easy. Okay, just use that agnostic interaction concept. Just use that agnostic interaction concept. See, this is titanium, CH3. Now you can see that in this complex we have beta hydrogens. That means in titanium eta 4 ET4 we have beta hydrogens. So on this complex we have 0 beta hydrogens. We have 3 right, 3 into basically right, we have 3 more groups, so 3 into 4. So we have this much amount of beta hydrogens, and in this case we have 0 beta hydrogens, and in this case we have 0 beta hydrogens. Okay, so this is highly unstable. Okay, this compound is highly unstable. So if it's unstable, so thermal stability of titanium ET4 should be least. Okay, it should be least, right? So we can cancel out option B and D. Okay, B and C. Next is, now the next thing over here is, right, so in this complex we have maximum beta hydrogens. Okay, so after beta hydrogens, for right, for unstability, right, for unstability, beta hydrogens plays the major role. Then after this beta hydrogens we have alpha hydrogens, then gamma hydrogens. So in this case you have maximum number of alpha hydrogens, and in this case you have right, 2 alpha hydrogens, and you have 2 alpha hydrogens. Okay, so in this case you have maximum number of alpha hydrogens. So so after T84, this group will come. Okay, this group will come, because in this case you have 1 2 3 4 5 6 7 8 9 10 11 12 alpha hydrogens. Okay, and in this particular group we have less number of alpha hydrogens. Okay, so the correct answer is basically option D. Okay, so is it clear to all of you? Is it clear? Okay, right, so option D is your correct answer. So this is the correct order of your stability or thermal stability. Okay, so now all right, fine. So just one question is left. Let's complete that question also, this one. Okay, so now what is the concept over here? So the concept is, so what is the name of this catalyst? Anyone, what is the name of this catalyst? No, don't have to see the factor of steric hindrance. Whenever you have beta hydrogens in any complex, that complex is highly unstable. If a number of beta hydrogens are same, then you can figure out, then you can just use steric factor concept. But before that, you have to use beta right, hydrogens. Yes, so this is Wilkinson's catalyst. Okay, this is Wilkinson's catalyst. Okay, so basically, you just have to understand the cycle of Wilkinson catalyst for hydrogenation. Okay, so how we can just draw for a Wilkinson catalyst only, you have to understand that, because it's very famous reagent. Okay, so we know this is your Wilkinson catalyst, PPH3, right, and Cl, then PPH3, and then PPH3. So what happens in first step, basically, right, it eliminates one PPH3. Okay, it eliminates one PPH3 in the first step. Okay, so all reactions are basically equilibrium reactions. Okay, so after this you basically have PPH3 and PPH and Cl ligand and PPH3. Okay, so these two ligands you have, basically PPH3 and Cl. Okay, so now it converts to this thing. So it's basically your elimination type of reaction. Okay, so it leaves this group and you have created one space. Okay, now if you have one space, so there's a possibility of oxidative addition. So what's going to happen? H2 will add on this rhodium. Okay, so PPH3 and then we have, right, chlorine, and then H2 will add on this group. Okay, so H2O will add and you have PPH3. Okay, so this is nothing but oxidative addition. You can see there's change in coordination number and oxidation state. Okay, so after this thing, right, so basically it's involved in hydrogenation of your alkenes, terminal alkenes. Okay, so after this thing there is addition of terminal alkenes. So let's take this is the terminal alkene. So this is converted to this system, chlorine, chlorine, then you have PPH3, hydrogen, hydrogen, and then you have PPH3, and then you have basically this alkene. So there is addition of this particular alkene. So right, so after this addition, okay, after this addition, so what's going to happen again, one PPH3 will leave the surface and it will convert this to this group. Okay, so basically what's going to happen, you have this RH and PPH3. Okay, it will take this hydrogen on this particular right, this particular alkene, and it will convert this alkene to alkane. Okay, and you have hydrogen and chlorine. So again it will just convert back to Wilkinson catalyst and it will release your alkane molecule. Okay, it will release your alkane molecule. So what's the function of your this Wilkinson catalyst? It hydrogenates your terminal alkene. So it converts your alkene to alkane. Okay, so that is the function of your Wilkinson's catalyst. Okay, so now you can just see what's the question. This is the cycle. So the question is, an efficient catalyst for hydrogenation of alkenes is Wilkinson's catalyst. However, if I change rhodium to iridium, does not catalyze this reaction. The reason, you can see, just figure out the reason from mechanism, that chlorine is present in initial stage and it's also present in final stage, and this chlorine is not basically going from the surface. So chlorine is in every step. That means chlorine is not making the difference. Okay, chlorine is not making the difference. I have explained it, right? Yes, it's important, and I have explained ferrocene in this session only, right? So chlorine is not important, so I can cancel out option B and D. Now, what is more important? PPH3. So if it's not catalyzing the reaction, or if it does not catalyze this reaction, it means basically, right, basically it binds stronger to iridium. If it's binds stronger to iridium, so this group won't leave. See, just see the first process. We have to make this group leave Wilkinson's catalyst. Okay, so if this bond is stronger, so this process is not feasible. So this bond should be weak. So in iridium, basically this PPH3 binds stronger to iridium than to rhodium. So that's why this reaction is not happening, or it's not catalyzing this process. Is it clear to all of you? Any doubts? Why option A is correct? Because in first step only you have to make PPH3 leave the Wilkinson's catalyst, and it's only possible if the metal PPH3 bond is weak. Okay, and that's only possible because basically if I just go by option, so PPH3 binds stronger to iridium, so then in that case this process won't be catalyzed, or this process is not possible. Okay, all right, so that's all about organometallics. Now the last point what I want to tell you is basically we have three right reactions or reaction mechanism: oxidative addition, reductive elimination, migratory insertion reaction. Right, these are basically three types of reactions that you have to study. And one more point, agostic interaction. So there is no need to refer any other material for JAM. You can just revise these notes. Okay, I'll post it on the Telegram channel, and just practice these questions, and you can just, or you can refer more questions, but the material is not required. This material is sufficient. Okay, this material is sufficient. Material is not required. If you want, you can practice more questions. Okay, so that's all about this class. I'll post this slide on the Telegram channel just after this class. Okay, so this is all about a quick revision of organometallics. Right, so I hope you found this session useful. If you did, you can just give it a big thumbs up. I'll just see you in the next class, and right, take care everyone. Bye bye.